On June 23, 1942, at approximately 14:30 hours, Royal Air Force personnel at Pembrey Airfield in South Wales observed a single Focke-Wulf 190A3 fighter aircraft executing a standard landing approach. The aircraft, identified by Luftwaffe markings as belonging to Jägerschwader 2, touched down on the grass runway and taxied to a stop near the control tower. The pilot, Oberleutnant Armin Faber, had become disoriented during combat operations over the English Channel and mistakenly believed he was landing at a German airfield in occupied France. This navigational error resulted in the delivery of an intact, operational FW-190 to Allied intelligence forces. The aircraft represented Germany's most advanced frontline fighter, a type that had been inflicting severe losses on RAF squadrons since its operational introduction in September 1941. Prior to this incident, Allied forces possessed no intact examples for technical evaluation. Every FW-190 previously shot down over Britain had sustained damage sufficient to prevent meaningful analysis of its flight characteristics and engineering solutions. The intelligence value of this acquisition proved substantial. Systematic testing at the Royal Aircraft Establishment, Farnborough, identified specific performance envelopes, operational limitations, and tactical vulnerabilities. This technical data was subsequently distributed to Allied fighter squadrons and influenced modifications to American fighter doctrine prior to large-scale operations over Europe. The information derived from Faber's aircraft directly affected tactical engagement protocols, pilot training curricula, and aircraft development priorities throughout the remainder of the conflict. The Focke-Wulf 190 entered Luftwaffe service with 2/JG-26 in August 1941, conducting its first operational sortie on September 1, 1941. The aircraft immediately demonstrated performance characteristics that exceeded those of the Supermarine Spitfire MKV, which constituted the primary RAF fighter defending British airspace and conducting offensive operations over occupied France. Initial combat reports from RAF pilots described an aircraft with superior speed in level flight and dive performance, exceptional roll rate, and concentrated firepower. Squadron leader J. E. Johnson, commanding No. 610 Squadron, filed reports in early 1942 noting that the FW-190 could consistently escape pursuing Spitfires through dive maneuvers and could reverse direction in rolling engagements faster than British pilots could maintain tracking solutions. RAF fighter command loss rates over France increased measurably following the FW-190's operational deployment. During the period January-June 1942, RAF fighter losses in cross-channel operations rose approximately 30% compared to the previous 6-month period. Combat reports indicated that FW-190 equipped units were achieving kill-to-loss ratios favorable to German forces, reversing the tactical balance that had existed during late 1940 and early 1941. Specific engagements demonstrated the problem's severity. During Operation Jubilee, the Dieppe raid of August 19, 1942, RAF forces lost 106 aircraft while German forces lost 48, with FW-190 units accounting for a disproportionate number of British losses. Pilot debriefings consistently identified the FW-190 as the primary threat, noting that existing tactical doctrine proved ineffective against the aircraft's performance envelope. RAF intelligence possessed limited information regarding the FW-190's technical specifications prior to June 1942. Photo reconnaissance provided external dimensions and armament configuration, but critical performance data remained unknown. Engine type, power output, maximum speed at various altitudes, service ceiling, and control characteristics could only be estimated through combat observation and pilot testimony. Every FW-190 shot down over Britain prior to Faber's landing had crashed with sufficient force to destroy or severely damage critical components. Recovered wreckage provided some information on construction methods and materials, but could not reveal flight performance characteristics. The inability to conduct controlled testing meant that RAF tactical bulletins contained recommendations based on incomplete data, limiting their effectiveness in reducing combat losses. Allied fighter limitations became increasingly apparent through operational experience. The Spitfire MKV, while possessing superior turning radius at most speeds, could not match the FW-190's acceleration, dive performance, or roll rate. American P-40 and P-39 fighters, then beginning to arrive in North Africa and the Pacific showed similar disadvantages. Without precise technical data on German capabilities, Allied air forces could not develop effective counterattacks or properly prioritize aircraft development programs. The captured FW-190A3 was powered by a BMW 801D2 14-cylinder, twin-row radial engine producing 1,700 horsepower at 2,700 revolutions per minute for takeoff. This represented approximately 230 horsepower more than the Rolls-Royce Merlin 45 installed in the Spitfire MKV, which produced 1,470 horsepower at 3,000 revolutions per minute. The power-to-weight ratio differential contributed directly to the FW-190's superior acceleration and climb rate below 20,000 feet. The BMW 801 utilized a sophisticated engine management system that automated mixture control, propeller pitch, and boost pressure adjustment. This system, designated Kommandojurat, reduced pilot workload during combat maneuvering and ensured optimal engine performance across varying flight conditions. British test pilots noted that the automated system provided consistent power delivery that simplified aircraft operation compared to manual engine management required in Spitfire variants. Testing revealed specific power characteristics across the operational envelope. Maximum speed at sea level was measured at 382 miles per hour. At 18,000 feet, the aircraft achieved 408 miles per hour. Rate of climb at sea level was documented at 2,350 feet per minute. These figures exceeded Spitfire MKV performance at equivalent altitudes by margins ranging from 25 to 40 miles per hour in speed and approximately 300 feet per minute in climb rate. The FW-190's most significant tactical advantage derived from its exceptional roll rate. The aircraft could execute a complete 360-degree roll in approximately 1.8 seconds at speeds between 250 and 300 miles per hour. The Spitfire MKV required approximately 3.5 seconds to complete the same maneuver. This difference proved decisive in combat, as the German pilot could reverse direction and establish firing position before the Allied pilot could complete a corresponding maneuver. The roll rate advantage resulted from several design factors. The FW-190 employed electrically actuated ailerons with high gearing ratios, providing light control forces across the speed range. Wing loading was distributed to optimize roll authority, with fuel tanks positioned close to the aircraft centerline to minimize rotational inertia. Control surface area and deflection angles were calculated to maximize roll acceleration without inducing excessive drag or control reversal at high speeds. Captain Eric Brown, Royal Navy, who conducted extensive flight testing of the captured aircraft, noted in his technical report, "The ailerons are exceptionally effective at all speeds. Control response is immediate and requires minimal physical effort. The aircraft can be thrown into violent maneuvers with ease, and recovery is equally straightforward. This represents a significant operational advantage in combat situations where rapid directional changes are required." The FW-190A3 carried 4 Mauser MG-151 20 cannons firing 20mm explosive shells, with 2 weapons mounted in the wing roots and 2 in the outer wing panels. Additionally, 2 Rheinmetall Borsig MG-17 machine guns firing 7.92mm ammunition were installed in the forward fuselage, synchronized to fire through the propeller arc. Total ammunition capacity was 200 rounds per cannon and 1,000 rounds per machine gun. Comparative analysis demonstrated substantial firepower advantages. The MG-151 20 fired at 740 rounds per minute with a muzzle velocity of 2,500 feet per second. A 2-second burst delivered approximately 50 rounds of 20mm ammunition, each projectile weighing 115 grams with explosive filler. The Spitfire MKV, by contrast, was armed with 2 20mm Hispano cannons and 4.303-inch machine guns, with the cannons having significantly lower reliability and ammunition capacity. Weapon placement provided tactical advantages. The concentration of armament near the aircraft centerline created a tight convergence pattern effective at ranges from 200 to 400 yards. This arrangement reduced the requirement for precise range estimation and allowed effective fire against targets during brief tracking opportunities. Test firing demonstrated that the weapon installation produced minimal recoil forces and did not significantly affect aircraft handling during sustained firing. The FW-190's airframe was designed for structural strength with an emphasis on dive performance. Maximum permissible speed was 560 miles per hour in a dive, substantially higher than the Spitfire Mkv's limit of 470 miles per hour. This capability allowed German pilots to employ dive tactics with confidence that pursuing Allied fighters could not maintain engagement. The aircraft's relatively heavy weight, 8,770 pounds loaded, contributed to dive acceleration. When combined with aerodynamic cleanliness and structural strength, this mass created a dive profile that consistently exceeded Allied fighter capabilities. RAF pilots reported that FW-190s could initiate dives from combat altitude and reach speeds that made pursuit impossible, effectively providing a guaranteed escape option in most engagement scenarios. Construction methods emphasized accessibility and maintenance efficiency. The engine installation could be removed as a complete unit in approximately 20 minutes using a wheel dolly system. Wing panel attachment points facilitated rapid component replacement. The cockpit layout concentrated instruments and controls for pilot efficiency, reducing cognitive workload during high-stress combat operations. These design decisions reflected German emphasis on operational readiness and sortie generation rates in deployed units. Following its arrival at the Royal Aircraft Establishment on June 25, 1942, the captured FW-190 underwent comprehensive evaluation according to standardized test protocols. The program consisted of 3 phases: ground examination and documentation, performance testing across the flight envelope, and tactical evaluation against representative Allied fighter types. Air Commodore Roderick Hill supervised the testing program with instructions to prioritize identification of operational weaknesses and tactical vulnerabilities. Initial ground examination documented all accessible components. Engine specifications, fuel system capacity, hydraulic systems, electrical systems, and control mechanisms were measured and photographed. Armament installation was examined in detail, with particular attention to ammunition capacity, feed mechanisms, and sight alignment. The cockpit layout was documented to understand pilot workload distribution and instrument presentation. This phase required approximately 72 hours of continuous work by technical specialists. Flight testing commenced on June 28, 1942, with initial familiarization flights conducted by Squadron Leader P. Shepard. Subsequent test flights expanded the evaluation envelope systematically, measuring maximum speeds at various altitudes, climb rates, turning performance, dive characteristics, and control response across the full range of operational speeds. Each test flight was documented with specific performance data and pilot observations recorded immediately after landing. The program generated approximately 40 hours of flight test data over a 3-week period. Testing revealed significant performance degradation above 20,000 feet altitude. The BMW 801 radial engine's supercharger system was optimized for low to medium altitude operation, with critical altitude for maximum boost pressure occurring at approximately 18,000 feet. Above this altitude, manifold pressure decreased progressively, reducing available power output. At 25,000 feet, horsepower output had decreased by approximately 25% compared to rated power at optimal altitude. This limitation manifested in reduced climb rate, decreased acceleration, and diminished maneuverability at altitudes above 20,000 feet. Climb rate at 25,000 feet was measured at 1,100 feet per minute, compared to 2,350 feet per minute at sea level. Maximum speed at 25,000 feet was 388 miles per hour, only marginally faster than performance at sea level and significantly slower than the Spitfire Mk9 equipped with the Merlin 61 engine, which achieved 416 miles per hour at the same altitude. The technical assessment concluded that the FW-190A3 was optimized for combat operations below 20,000 feet, where its power advantages provided decisive tactical benefits. Above this altitude, the performance differential narrowed substantially, and later model Spitfires equipped with 2-stage supercharged engines possessed superior performance. This finding had immediate implications for tactical doctrine, suggesting that Allied forces could gain advantage by forcing engagements to higher altitudes where German fighters could not exploit their low-altitude superiority. While the FW-190 demonstrated excellent control harmony at normal combat speeds, Testing identified increasing control forces at velocities exceeding 400 miles per hour. At speeds approaching the aircraft's maximum dive velocity, elevator forces required to initiate pull-out maneuvers became substantial, demanding significant physical strength from the pilot. Specific measurements documented this characteristic. At 450 miles per hour, executing a 4G pull-out required approximately 50 pounds of stick force. At 520 miles per hour, the same maneuver required approximately 80 pounds of force. This created a vulnerability during the recovery phase of high-speed dives. If an Allied fighter could maintain pursuit through the initial dive segment, the German pilot faced a period during pull-out when control inputs demanded maximum physical effort, potentially degrading situational awareness and defensive maneuvering capability. Test pilots noted that this characteristic was not immediately apparent during normal combat maneuvering but became significant during extended high-speed operations. Captain Brown's report stated, "Recovery from high-speed dives requires considerable physical effort. A pilot executing repeated dive-and-recover tactics would experience fatigue that could affect performance during subsequent combat. This represents a potentially exploitable vulnerability if Allied pilots can maintain pursuit through the dive phase and engage during the recovery when the German pilot is managing heavy control loads." Comparative testing against the Spitfire MKV demonstrated that while the FW-190 possessed superior roll rate and initial turn performance, it could not maintain tight turning radius during sustained horizontal maneuvers. The aircraft's higher wing loading, 36.9 pounds per square foot compared to the Spitfire's 24.9 pounds per square foot, required higher speeds to maintain lift in level turns. At combat speeds of 280 miles per hour, the Spitfire MKV could sustain a turning radius approximately 15% tighter than the FW-190. This advantage became more pronounced as airspeed decreased. At 200 miles per hour, the Spitfire's turning radius was approximately 25% tighter. If a German pilot could be forced into sustained horizontal turning combat at reduced speeds, the tactical advantage shifted to the Allied fighter. However, this weakness could be negated by the FW-190's superior roll rate and acceleration. German pilots trained to avoid sustained turning engagements, instead employing high-speed slashing attacks that leveraged the aircraft's strengths. Combat reports indicated that experienced FW-190 pilots rarely allowed themselves to be drawn into prolonged turning battles, using vertical maneuvers and rapid direction changes to maintain initiative. The captured aircraft testing therefore emphasized that Allied pilots needed to force engagement conditions that prevented German pilots from employing preferred tactics. Systematic comparison testing produced a comprehensive performance matrix that quantified the relative capabilities of the FW-190A3 and Spitfire MKV across multiple parameters. At altitudes below 15,000 feet, the FW-190 held advantages in maximum speed, 20 to 30 miles per hour, climb rate, 200 to 300 fpm, roll rate, approximately 2-to-1 ratio, and firepower concentration. The Spitfire demonstrated advantages in sustained turning radius, 15 to 25%, and operational ceiling. At altitudes between 15,000 and 20,000 feet, performance differentials narrowed. The FW-190 maintained roll rate and firepower advantages, but speed and climb margins decreased. Above 20,000 feet, the Spitfire Mk9 equipped with the Merlin 61 engine demonstrated clear superiority in all performance parameters except roll rate. These findings were documented in Technical Intelligence Report Air 2/7563, distributed to RAF Fighter Command on July 15, 1942. The report concluded, "The FW-190 represents a formidable opponent below 20,000 feet, when flown by competent pilots employing appropriate tactics. Allied fighters can exploit high-altitude performance advantages, sustain turning capability at reduced speeds, and vulnerability during high-speed dive recovery. Tactical doctrine should emphasize engagement conditions that negate German strengths while maximizing Allied capabilities." RAF Fighter Command maintained a standardized system for distributing tactical intelligence to operational squadrons. Following completion of the FW-190 evaluation, Air Vice Marshal Trafford Leigh-Mallory directed immediate dissemination of findings through Tactical Memorandum No. 8, issued on July 20, 1942. This document was distributed to all fighter squadrons in Fighter Command and forwarded to RAF Middle East Command and units operating in the Mediterranean theater. The memorandum provided specific tactical recommendations based on test results. Pilots were instructed to avoid low-altitude engagements when possible, forcing German fighters to climb to altitudes above 20,000 feet where RAF aircraft held performance advantages. When engagement at low altitude was unavoidable, pilots were advised to exploit the FW-190's limitations in sustained turning combat, attempting to force horizontal maneuvering at reduced speeds rather than vertical rolling engagements. Additional guidance addressed pursuit tactics during dive escapes. The memorandum noted that while FW-190s could outdive Spitfires initially, the German aircraft's heavy controls during pull-out created vulnerability windows. Allied pilots were instructed to maintain pursuit through the dive phase and attempt engagement during recovery when the FW-190 pilot would be managing high control forces and potentially experiencing reduced situational awareness. The bulletin system included provisions for feedback from operational units. Squadron intelligence officers were directed to collect combat reports specifically addressing FW-190 engagements, with emphasis on validating or refining the recommended tactics. This information was compiled monthly and analyzed to identify emerging patterns or tactical innovations developed by field units. The system created a continuous improvement cycle that allowed doctrine to evolve based on operational experience. In August 1942, the United States Army Air Forces dispatched a technical evaluation team to the Royal Aircraft Establishment specifically to examine the captured FW-190. The team included Major Cass Hoff, an experienced fighter pilot assigned to the 8th Fighter Command, and several technical specialists from Wright Field Material Command. The team spent 10 days conducting flight evaluations and reviewing British test data. Major Hoff flew the FW-190 for approximately 6 hours, conducting performance testing and tactical evaluation flights against RAF Spitfires and American P-47 Thunderbolts that were beginning to arrive in Britain. His assessment was documented in Report No. TSEIA 5-703A, submitted to 8 Fighter Command Headquarters on August 28, 1942. The report's conclusions were unequivocal. The FW-190 will defeat any Allied fighter in combat below 20,000 feet if the German pilot employs proper tactics. American fighters possess advantages at high altitude. Tactical doctrine must exploit these advantages and avoid engagement conditions favorable to the enemy. Hoff's report included specific recommendations for P-47 operations. The Thunderbolt possessed excellent high-altitude performance due to its turbocharged engine, capable of maintaining full power to altitudes exceeding 30,000 feet. However, at low altitude, the P-47 was slower than the FW-190 and less maneuverable. The report recommended that P-47 units operate at maximum practical altitude, using altitude advantage to control engagement initiation and forcing German fighters to climb into unfavorable combat conditions. The American assessment differed slightly from RAF conclusions in emphasis. While British doctrine focused on forcing turning engagements, American evaluation stressed altitude advantage as the primary tactical consideration. This reflected differences in aircraft capabilities and operational requirements. The P-47, with its excellent high-altitude performance but greater weight and lower maneuverability, was better suited to energy tactics employing altitude and speed rather than turning combat. This distinction influenced how each air force incorporated the intelligence into operational doctrine. The 8th Fighter Command implemented doctrinal changes based on the FW-190 evaluation during the autumn of 1942, prior to commencing large-scale fighter operations over Europe. Training programs at P-47 operational training units in Britain incorporated specific modules addressing engagement with FW-190s, emphasizing altitude discipline and energy management tactics. Standard operating procedures for bomber escort missions specified minimum operating altitudes of 25,000 feet for fighter formations. When German fighters attempted to engage bomber formations at lower altitudes, P-47 escorts were instructed to maintain altitude advantage and execute diving attacks, using speed accumulated in the descent to engage German fighters and then climbing back to altitude rather than pursuing into extended low-altitude combat. Fighter sweep missions operated under similar principles. P-47 formations typically cruised at 28,000 to 32,000 feet, deliberately presenting themselves as targets to German fighters below. When German units attempted to climb to engage, American pilots could observe their ascent and either maintain altitude advantage or execute high-speed diving attacks timed to catch German aircraft during their climb when their energy state was compromised. The doctrine revision included explicit prohibitions against certain tactical behaviors. Pilots were instructed not to follow FW-190s into dives unless maintaining speed advantage, not to attempt sustained turning combat at low altitude, and not to attempt to outroll German fighters in rolling scissors maneuvers. These prohibitions were based directly on performance testing of the captured aircraft and represented a significant shift from pre-war American fighter doctrine that had emphasized turning combat and low-altitude operations. Operational training units modified curricula to incorporate FW-190 specific tactical instruction. The 56th Fighter Group, the first P-47 unit to become operational in Britain, received briefings that included detailed presentations on the captured aircraft's capabilities and limitations. Training flights included simulated engagements where instructors flew profiles representing FW-190 performance, allowing pilots to practice the recommended tactical responses in controlled conditions. Film presentations developed by RAF intelligence showing the captured FW-190 in flight were incorporated into ground school instruction. These films demonstrated the aircraft's roll rate, dive performance, and climbing characteristics, providing pilots with visual reference for what they would encounter in combat. The presentations included comparative footage showing Spitfires attempting to match FW-190 maneuvers, illustrating the performance differentials that pilots needed to account for in tactical decision-making. Intelligence officers assigned to fighter groups maintained updated information on FW-190 variants as they appeared in combat. When the FW-190A-4 entered service in late 1942 with minor improvements, and subsequently when the A-5 and A-6 variants appeared in 1943, technical bulletins provided updated specifications. This system ensured that tactical recommendations remained current as German aircraft evolved. The foundation established through examination of Faber's captured aircraft provided the baseline against which all subsequent variants were evaluated. Analysis of combat loss statistics demonstrates measurable changes in engagement outcomes following distribution of intelligence derived from the captured FW-190. During the first 6 months of 1943, as American P-47 units began operations over Europe employing revised tactical doctrine, loss rates among 8 fighter command units remained lower than RAF experienced during equivalent phases of earlier operations. Specific data from the 56th Fighter Group, which became operational in April 1943, illustrates this pattern. During its first 3 months of combat operations, the group claimed 33 German aircraft destroyed while losing 11 P-47s in air combat, representing a kill ratio of approximately 3-to-1 in favor of American forces. This compared favorably to RAF experience during early 1942, when Spitfire squadrons typically achieved ratios closer to 1-to-1 against FW-190-equipped units. By late 1943, following introduction of the P-51 Mustang equipped with the Merlin engine and wider adoption of high-altitude tactical doctrine across all American fighter units, kill ratios improved further. The 4th Fighter Group, operating P-47s and later P-51s, achieved a cumulative kill ratio of approximately 4-to-1 for 1943 to 1944 operations. German records indicate that Luftwaffe units were experiencing unsustainable loss rates by the spring of 1944, with pilot replacement failing to keep pace with losses. These statistical improvements cannot be attributed solely to intelligence gained from the captured aircraft. Introduction of improved Allied fighter types, increasing numerical superiority, declining German pilot quality due to training time reductions, and fuel shortages affecting Luftwaffe operations all contributed to shifting kill ratios. However, the tactical doctrine that allowed American pilots to engage German fighters effectively from the beginning of large-scale operations was based directly on performance analysis of Faber's FW-190. Operational experience validated the tactical weaknesses identified during testing at Farnborough. Combat reports from 1943 to 1944 document numerous instances where Allied pilots successfully employed high-altitude tactics to negate FW-190 advantages. American fighter formations operating at 28,000 to 30,000 feet routinely forced German fighters to climb to altitude, where Allied aircraft held performance superiority. Lieutenant Colonel Hubert Zemke, commanding the 56th Fighter Group, described the tactical application in a post-mission report from August 1943. German fighters attempted to engage our formation at 25,000 feet. We maintained altitude and executed diving attacks, using speed advantage to engage and then climbing back to altitude. German aircraft could not follow us through the climb. We achieved 3 confirmed without loss. The tactical principle is sound and repeatedly validated in combat. RAF squadrons similarly exploited the sustained turning weakness identified in testing. Combat reports from late 1942 and 1943 describe Spitfire pilots successfully forcing FW-190s into horizontal turning engagements at reduced speeds, where the Spitfire's lower wing loading provided advantage. Squadron leader J.E. Johnson, by then commanding a Spitfire wing, noted in his combat journal that forcing the 190 to fight our fight rather than his consistently produces favorable results. The vulnerability during high-speed dive recovery proved more difficult to exploit operationally. Maintaining pursuit through a full-power dive required significant pilot skill and aircraft capability. However, several documented instances demonstrate successful application of this tactic. Combat reports describe Allied pilots maintaining pursuit through FW-190 dive escapes and achieving firing positions during pull-out when German pilots were managing heavy control loads. While this remained a challenging maneuver, the knowledge that such pursuits were potentially successful prevented German pilots from treating the dive as an automatic escape option. German fighter units observed changes in Allied tactical behavior during 1943 and adapted their operations accordingly. Luftwaffe combat reports from this period note that American fighters were maintaining disciplined altitude advantage and refusing to be drawn into low-altitude combat. Oberst Egon Mayer, commanding JG-2, issued tactical guidance in September 1943 instructing pilots to avoid climbing to engage high-altitude American formations, instead focusing on bomber formations at lower altitudes where German fighters retained performance advantages. Major Joseph Priller, commanding JG-26, noted in his unit history that American pilots have clearly received instruction on the 190's capabilities and limitations. They no longer make the tactical errors that allowed us such success in 1942. They force us to fight at high altitude where their aircraft perform better, and they refuse to follow us into dives or rolling maneuvers where we hold advantages. These observations from German sources confirm that the intelligence derived from the captured aircraft had affected Allied tactical behavior in ways that German pilots recognized. The adaptation represented a significant shift in the tactical balance of air combat over Europe. While German pilots remained individually skilled and their aircraft remained competitive, the intelligence advantage held by Allied forces contributed to gradually shifting the operational balance in favor of American and British air forces. Technical analysis of the captured FW-190 influenced Allied aircraft development programs, though the extent of this influence varied across different projects. American engineers at Wright Field examined the aileron design and control system configuration, seeking to understand the source of the FW-190's superior roll rate. While the P-47 could not be substantially modified due to its advanced development stage, these insights influenced design decisions for later aircraft. The P-51 Mustang underwent aileron modifications in 1943, partially informed by analysis of the FW-190's control system. Engineers modified the aileron balance and reduced control friction, improving roll rate by approximately 15%. While still not matching the FW-190's performance in this parameter, the improvement was operationally significant. Test pilot reports indicated that the modified P-51 could maintain more competitive performance during rolling maneuvers against German fighters. The FW-190's armament configuration influenced American thinking about gun placement and ammunition capacity. The concentration of weapons near the fuselage centerline demonstrated advantages in reducing convergence problems, and later American aircraft designs incorporated this principle more consistently. The Republic P-47N and North American P-51H featured improved gun installations that reflected lessons learned from examining the German aircraft's weapon system. British aircraft development was similarly influenced. The Hawker Tempest, which entered service in 1944, incorporated design elements addressing weaknesses observed in earlier aircraft when compared to the FW-190. The Tempest featured improved roll rate through modified aileron design, higher maximum dive speed through strengthened structure, and concentrated armament installation. While these design decisions resulted from multiple influences, analysis of the captured FW-190 provided specific technical data that informed engineering choices. The captured FW-190A3 remained at the Royal Aircraft Establishment throughout the war, serving as a reference aircraft for evaluating subsequent German fighter variants. When the FW-190A8 appeared in 1944 with increased armament and armor, British engineers compared it directly to Faber's original aircraft to understand the modifications. Similarly, when the FW-190D9 entered service in late 1944 with an inline Junkers Jumo 213 engine addressing the high-altitude performance limitations, intelligence officers could immediately assess how this variant corrected the weaknesses identified in the original radial engine version. The availability of an intact, flyable example also facilitated training and demonstration. Selected pilots from operational units were given orientation flights in the captured aircraft, providing direct experience with German fighter characteristics. These pilots returned to their units with detailed knowledge of how German aircraft handled, improving their ability to anticipate enemy maneuvers and train less experienced pilots. Post-war assessment by RAF intelligence concluded that the intelligence value of Faber's aircraft was among the highest of any single intelligence acquisition during the conflict. Air Vice Marshal Victor Goddard, writing in 1946, stated, "The detailed technical and tactical intelligence derived from comprehensive examination of the intact FW-190 provided information that directly influenced operational doctrine, training programs, and equipment development. The intelligence impact extended across multiple years and affected thousands of combat operations. The strategic value of this single aircraft exceeded that of many large-scale intelligence operations involving substantially greater resources. The accidental delivery of Oberleutnant Armin Faber's Focke-Wulf 190A3 to Royal Air Force custody on June 23, 1942, represents a significant case study in the relationship between technological capability and intelligence information in modern warfare. The incident demonstrated that technological superiority, while operationally significant, can be substantially negated through systematic analysis and tactical adaptation based on accurate technical intelligence. The FW-190's initial operational success during September 1941 through June 1942 derived primarily from performance advantages that Allied forces could not counter due to incomplete understanding of the aircraft's capabilities and limitations. Once systematic testing provided precise data on performance envelopes, control characteristics, and operational weaknesses, Allied air forces developed tactical doctrine that exploited these weaknesses while minimizing exposure to German strengths. The resulting shift in engagement outcomes demonstrates the multiplying effect of accurate technical intelligence on operational effectiveness. The case also illustrates the importance of intelligence distribution systems and doctrinal flexibility. The technical data derived from testing at Farnborough was valuable only to the extent that it reached operational units in usable form and was incorporated into training and tactical procedures. The RAF's Tactical Bulletin System and the American Fighter Command's training modifications demonstrate effective intelligence utilization, converting technical data into operational advantage through systematic dissemination and implementation. Several factors contributed to the intelligence value of the captured aircraft. The aircraft's intact condition permitted comprehensive testing impossible with damaged examples. The timing of the acquisition, occurring before large-scale American fighter operations commenced over Europe, allowed American doctrine to incorporate lessons learned rather than requiring doctrinal revision after operational experience demonstrated existing tactics were inadequate. The systematic nature of the testing program, which prioritized identification of weaknesses rather than merely documenting capabilities, produced actionable intelligence rather than descriptive technical data. The FW-190 case demonstrates principles applicable to broader analysis of technology and intelligence in warfare. First, technological advantage is contextual rather than absolute. The FW-190 dominated at low altitude but was inferior at high altitude. Allied forces exploited this by forcing engagements into altitude regimes where their aircraft held advantages. Second, tactical doctrine can compensate for technological disadvantage when based on accurate intelligence. American and British pilots operated aircraft that were individually inferior to the FW 190 in several parameters but achieved favorable operational outcomes through tactics that exploited specific weaknesses. Third, intelligence value depends on systematic analysis and effective dissemination, not merely on acquisition of information. The historical significance of Faber's navigation error extends beyond its immediate tactical implications. The intelligence windfall influenced Allied fighter operations throughout 1943 to 1945, affected aircraft development programs, and provided a foundation for evaluating subsequent German fighter variants. The case demonstrates that in technological competition between adversaries, intelligence regarding opponent capabilities can prove as significant as development of superior equipment. Understanding how an opponent's technology works, what its limitations are, and how those limitations can be exploited operationally provides advantages that may equal or exceed those gained through purely technological innovation. The Focke-Wulf 190 remains recognized as one of the most significant fighter aircraft designs of the Second World War, notable for its engineering sophistication and operational effectiveness. However, its historical impact is inseparable from the circumstances that allowed Allied forces to examine it systematically and develop effective countertactics. The aircraft that terrorized Allied pilots during 1942 became, through Faber's error and systematic Allied analysis, a teaching tool that contributed to the eventual Allied air superiority over Europe. The case illustrates the complex interplay between technology, intelligence, and operational adaptation that characterizes modern warfare, where information about enemy capabilities may prove as decisive as the capabilities themselves.